So now we're going to examine what happens when you have work that is done by forces that are not uniform. We've looked at gravity, which is a uniform force, or applied forces, thrust or other things like that. But there are some forces that are not uniform. That is to say that the value of the force actually depends on the distance, or it just changes. It's difficult for a person, if they're pushing something, to apply a force uniformly. So we have to have a little bit of a different approach when we deal with forces that are not uniform. And we'd like to start by looking at the simplest situation, or the I guess most straightforward, and one in which we can actually come up with an equation for calculating the work done, and that is for springs. So the formula for the force on a spring is F is equal to minus kx, where x is the displacement of the spring. So essentially, as you increase the displacement of the spring, then it requires greater force. So the first, let's say, centimeter of compressing a spring requires less force than the second centimeter. The third centimeter requires even more. And as a result, you don't have a constant force. So as the spring is changing, and so of course there's the displacement for the work, for the F times D, there's the D, but the F is increasing as you increase the displacement. So then that creates like a little bit of a complex situation. So in order to address that, the easiest way to think about it is to look at a graph of force versus displacement. So before we look at what happens with the non-uniform, let's look at uniform. So let's say, for example, that you apply a constant force over some displacement. Then the work in that case would be represented by the area of the graph. Because, as we all know, F times D is W, the work. So in this situation, it's pretty simple, and I mean, honestly, there's probably no reason to even look at the graph if you have a constant force, because it's just simply F times D. The graph doesn't really add anything to it. It doesn't really, it's conceptually maybe interesting that the area of the force times displacement graph allows you to calculate what the work is, but it's not really necessary. On the other hand, for a spring, the F versus D graph looks a little bit different. And for our purposes, when I say D, that's the same thing as the X up here. So the displacement that we're talking about right here is it's the same as the D. And essentially the way an F versus D graph looks like is a straight line like this. So in this case, it is still true that the work is equal to the area of the graph, but obviously the shape of the graph has changed, so we need to modify our formula a little bit in order to be able to calculate the area. So obviously we have a triangle, and the area of a triangle is 1/2 base times height, so that would be 1/2 the displacement times the force, or the maximum force. So I would say that W is equal to 1/2 F times D. And so, we could look at any kind of shape that we want to, but this shape, this particular one, because it's a simple relationship, it's a direct proportion between force and displacement, that is going to allow us to create a new equation which is specific to the elastic energy. So this would be good for rubber bands, for springs, obviously, for bungee cords, for anything that's elastic that follows Hooke's law. Not all objects follow Hooke's law, but in general, springs, especially metallic springs, they do follow Hooke's law pretty faithfully. So if you imagine that the formula for force is K times X, then I can make a substitution down here for F, and that would look like this. W is equal to 1/2 K times, in this case, X, and times D again, which is the same thing as X, that's the displacement, And so we end up with a new version of the equation. This is for elastic energy, that it is 1/2 kx squared. So a little bit like the kinetic energy formula, 1/2 mv squared, but in this case 1/2 kx squared. K being the spring constant, essentially a measure of the strength of the spring, and x being the displacement of the spring. So just to point out how this would actually work, if you displace the spring from its origin, then it's pretty straightforward. You're just going to calculate the area of the thing, or alternatively you can just use the equation. But if I do something like this, if I ask you to calculate how much work was done in stretching the spring from one point, which is not at the zero, to some other point which is also not the zero, then that creates a little bit of a problem. Let's say, for example, this was 10 and this was 4. So it might seem like what you would want to do is to subtract these two. So 10 minus 4 would be 6, and then that's what you would use for your base. But that is not going to give you the correct answer, because when you square that, that does not give you the same answer as you would get if you do the technique that I'm going to show you. So the way to think about it is you need to plug in both of these, and so the work, or the change in elastic energy, is going to be the total energy that you get by compressing the spring all the way, right? So that's this big triangle. And then if you were to subtract out the little triangle, what would be left is this trapezoid-shaped triangle. So for this one, we want to take the big triangle minus the little triangle to get the trapezoid-shaped portion. So the way that would look in terms of the equation is, we would say that, let me do it under here actually. We would say that the work done would be 1/2 kx squared minus 1/2 kx naught squared. That's just like the same thing you would do with the kinetic energy. If you were trying to calculate the change in kinetic energy, you wouldn't subtract the two velocities and then square it. You would have to square the two velocities first. That's the order of operations. You would square the two velocities first, and then you would subtract. The same thing occurs when you do this with the spring. So the values of the two extensions need to be plugged in first and squared. Now you could factor out the x squared, so 1/2 k times the quantity x squared minus x naught squared. That would be fine. But you must square the extensions first before you then go ahead and multiply by the 1/2 k. So just to summarize, for this particular non-uniform force, we get an equation for elastic energy, which I will call EE. You can call it W also. There's no problem with that. You can say the work done on the spring, or the work done by the spring, and that is 1/2 kx squared. Most of the time, we will not be concerned about the elastic energy. We'll be concerned about the change in the elastic energy, much like the way we do with the kinetic energy. We don't worry ourselves too much about what the kinetic energy is, but how much the kinetic energy has changed, and where did that energy go to. So let's take a look at an example problem. And we'll start off with this issue of what happens when you have them the spring is not starting from the origin, but from some point that it's already where it's already partially compressed or partially stretched. So in calculating the work done, I would say that W is equal to 1/2 kx squared minus 1/2 kx naught squared. So this is 1/2 times 120. Now, just to remind you, we could factor out the x squared minus the x naught squared, which I am going to do, but there's one issue, and that is that the units for the spring constant were given in newtons per meter, and that means that the units for the extension must also be in units of meters. So I'm going to convert this to meters, 0.5. 5 is the final extension of the spring. That's squared minus 0.03 squared. And then we can go to the calculator. So that is 0.05 squared minus 0.03 squared. And then multiplied by 0.5 times 120 to get 0.96. So the work is equal to 0.096 joules. And just to remind you graphically, how would that look? Here's 5. 3 would be somewhere around here. And the area that we want is this one. So if you just look at how the equation worked out, I did 1/2 120 times 0.05 squared. That's the big triangle. That's the whole thing. And I subtracted from that 1/2 times 120 times 0.03 squared. That's the little triangle. So if I subtract the little triangle from the bigger triangle, what I get left with is the trapezoid that's there in the underneath. Now, obviously, one thing that I could have done is if I was just looking at the graph, and let's say I didn't know what the spring constant was, and I didn't want to waste time figuring out what it is, what I could have also done is just use the values from the graph. You know, obviously this is a trapezoid, so the alternative way of doing it would be to say that W is equal to 1/2, and in this case it would be the, so trapezoids could look like this, where these would be bases, so I get base 1 plus base 2, right? And then I would cut that in half, and I would multiply that by the height. Or we can turn trapezoids on their ends like this, and what was previously a base is now a height. So I could say F1 plus F2 times the x, which is the base right here. Now I don't have the numbers for these. I mean, I can certainly calculate what the values would be, but if I did not have the spring constant, but I had the graph, I probably would do it this way because it's quicker than trying to calculate the spring constant, which obviously I could do with this graph. But if I'm not being asked for the spring constant, then there's no point in wasting time getting that. I can just look at the area, and essentially you're only going to be asked to deal with 3 kinds of areas. So 1 would be a rectangle, which is simple and easy to take care of. 2 is a triangle, and 3 is a trapezoid. We're not going to look at any strange or weird or awkward shapes that don't have some kind of simple geometric formula for making their calculation. Okay, so now we'll apply the spring to doing something useful, and in order to do that, then instead of just calculating how much work is done on a spring or by a spring, we're going to use the work that was done by the spring to convert to kinetic energy, which would be a common thing that we want to do with the energy that we've stored in a spring. So in this case, ultimately what's going to happen is we're going to transform elastic energy into kinetic energy. So EE turns into EK. We're going to compress the spring with a little toy dart. We'll get pushed into the gun. It'll compress a spring, and then we're going to release the spring, and the spring is going to convert all that elastic energy into the kinetic energy of the dart. And in this case, we're going to look at it without friction. We're going to assume that it is a complete transformation of elastic energy into kinetic energy. And we've already talked about the formula, 1/2 kx squared equals 1/2 mv squared. Here's a rare case where both of the energies actually have the number 1/2. So we can just get rid of that by multiplying by 2. And since in this problem we are looking to determine the speed of the dart as it leaves the gun, then we want to solve for v, and so obviously we'll have to take the square root of kx squared over m. In this particular problem, we won't have to worry about subtracting out the initial position of the spring because the initial position of the spring was 0. It had no compression at all. And so we can just plug in the final compression of the spring and not worry about subtracting out that other energy. So in this case, the spring constant turned out to be 60, and that would be times 0.035 squared. And then that's all divided by 0.025. So calculating the final answer, 60 times 0.035 squared equals, divided by 0.025, and then taking the square root. So we get 1.71 meters per second. Just like we might do with a potential energy problem. You know, we drop an object and we want to know how fast is it going to be going just before it hits the ground, or we want to know how fast is that roller coaster going at the bottom of the first hill. And in those cases, we transform potential energy into kinetic energy, and this is just the same idea, except that the form of potential energy that we're talking about is elastic potential energy, and so it's just a slightly different formula to calculate its value. However, it is very likely that in the real world that there would be some friction present. And so let's look at how does that work out when you actually are forced to take into consideration the frictional forces that might be acting on the object. So we're going to recalculate the exit speed, but this time we're going to take into consideration a small frictional force that's acting on the object in order to make it a little bit more realistic. There's kind of two ways of thinking about this problem. I think really the most accurate way of thinking about it is like this. We have elastic energy, but because friction is going to act on this object, we will not get all of that energy back. So some of that energy will be taken away or stolen away by the work done by friction. And when friction does work, it mostly turns that energy into a little bit into sound, but most of it goes into heat. And once it's turned into heat, the heat escapes to the air and then it never comes back. So this is, again, one of the reasons why frictional forces are considered to be non-conservative forces, because once you turn that energy into the heat from friction, it never comes back to you again. So it can't be returned back into either elastic or potential or kinetic in the way that those conservative forces can oscillate back and forth between one form of energy to the other, as we saw with the spring. So this guy can go back and forth, constantly transforming the energy from elastic potential energy to gravitational potential energy to kinetic energy. And without friction or drag, that will just continue on forever. So the way to think about it is that the elastic energy, in order to know how much was converted into kinetic energy, what we need to do is to subtract out the work from friction, because that energy will never come back. And then whatever remains, whatever is left over, that energy gets turned into our kinetic energy. That's maybe a little bit more accurate way of thinking about it, but to me, the way I generally think about it is like this. We have elastic energy to start with. It's all elastic energy. The dart is compressing the spring. All of the energy is in the form of elastic energy. I know that elastic energy is going to be converted at least somewhat into kinetic energy, but then also some of it will be turned into this non-conservative form of energy, the work due to friction. But these two forms of energy combined must be the same as the total of the kinetic energy. So it's still essentially a conservation of energy problem, even though part of the energy is going to go away, never to come back again. But at least for this example, I'm going to be able to calculate the velocity. So I'm going to go ahead and just use this formula, and that says 1/2 kx squared is equal to 1/2 mv squared plus, and you can see the two equations are, they're exactly the same equation, plus f of f times d. Now in this case, the d is exactly the same d here as it is for over here. So the distance that you compress the spring, that's also the distance along which the frictional force is going to be able to act. And just to remind you from the previous problem, that compression was 3.5 centimeters. 3.5 centimeters, the mass of the dart is 0.025, and the spring constant is 60 newtons per meter. I could multiply by 2, and that would get rid of the 1/2, but I don't really see how that's a big advantage, so I'm just going to leave those as they are. 1/2 60 times 0.035 squared equal to 1/2 0.025 times v squared plus 0.30, that's the frictional force, times the displacement, which is 0.035. So I'm going to calculate each of these three numbers separately. So 60 divided by 2 is 30 times 0.035 squared, and that is 0.03675. This guy, 1/2 times 0.025 is 0.0125 v squared, and 0.3 times 0.035 is 0.0105. Okay, so all I'm going to do is first move this over to the other side by subtracting that. And so that leaves me with the left side 625, and that is equal to 0.0125 v squared. So therefore we can divide that number divided by 0.0125, and that gives me 2.1, and then we'll take the square root, and that gives me 1.4 meters per second. So a little bit lower than the velocity we found before, because in the previous one we found the velocity was 1.7 meters per second. Now we add a little bit of friction and we get a little bit less speed from it, but still fundamentally the same kind of problem. We're just looking at kinetic energy. The kinetic energy of the elastic energy of the dart gets turned into kinetic energy, and as a result we basically solve all problems with elastic energy in the same way we would solve any of the other conservation of energy problems, even though the force is considered to be non-uniform. Using this formula, 1/2 kx squared, we can solve any problem involving a spring.